Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, everybody, welcome. And we'd like to say hello to Michael Ernst, who a lot of us know. He has Northwest past, being an alum of both Microsoft Research and the UW, where he got his PhD. He's been at MIT for approximately the last 6 years, and he's going to tell us about some of his work going on there on inference.
Thanks very much. It's a real pleasure to be here. Thanks for having me. So if you have questions during the talk, I encourage you to interrupt, because I'd much rather that you understand what's going on than that I get through every last slide. I'm going to ask your indulgence, because I can't resist telling you a little bit about some of the other projects that I wasn't able to talk about today. And if people are interested in these, I'd be delighted to tell you about them afterward. So essentially, my group, the Program Analysis Group, is interested in ways to improve programmer productivity. We're interested in software engineering. And you could divide our work into 4 general areas: programming language design and type theory, security, dynamic analysis, and testing. So on the programming language design and type theory side, we've done some work on parameterizing Java classes, that is turning a non-generic code into generic code, like converting your C# version 1 into C# version 2 code. Java is not quite as clean as C#. We're able to automatically add type parameters, and it actually does better than human experts, according to the human experts. I'm also Java's annotations are similar to C#'s attributes. They can be attached to declarations, but they can't be attached to arbitrary uses of types in a program. And that means users can't define their own type qualifiers. So Java Specification Request 308, which will be part of Java 7, actually adds that capability to Java, and I'm hoping that C# will be extended in a similar way as well. So that way, people can define their own type qualifiers like non-null or interned or read-only, and get a compile time guarantee. So the motivation for that was our type system for reference immutability. The type system guarantees that given a read-only reference, the code does not change the abstract state of the object referred to, which includes anything that's transitively reachable. And we have 160,000 lines of code written in this language. It's found and prevented errors. And I'm going to talk to you today about inferring abstract types. So we're doing some work in security. If any of you had a chance to talk to my student, Stephen McCammett, yesterday, he told you about the second one. These are actually both work that he's done. In the first one, he extended software fault isolation to the x86 architecture. People have done it for RISC machines before, but there are a number of new challenges for CISC machines. For example, x86 has instructions of varying length. If you jump into the middle of an instruction, even if it's the sort of place that you should be allowed to execute, you can interpret that, then the bytes can be interpreted in some different way and have a bad effect. So you have to make sure that all of those jumps are aligned. His current work is on information flow tracking. You have a program that takes some private inputs and some public inputs. The question is, how much information about the private inputs is leaked in the output of the program? So his work is different than other work in 3 respects. First, it works on real programs written in existing languages. It doesn't require you to rewrite your entire system. The biggest piece of code that he's annotated so far is a 500,000-line Objective-C program. The second way it's different is that there are no trusted annotations. In other words, everything's checked. And third is it doesn't tell you yes or no, but it actually gives you an estimate, an overestimate of the specific number of bits, like this program leaks 57 bits. Some dynamic analysis work, something that some of you may know is my work on dynamic invariant detection. It's machine learning. You observe a program executing, see what values it computes, and generalize from those to get a specification for the program. There are now 3 companies that are commercializing this, and there are lots and lots of academic users, so that's very nice. Another piece of work is on data structure repair. If data structures become corrupted, if you know what the spec is, then sometimes the right thing to do is to terminate your program immediately, because it might do something terrible. On the other hand, if it's providing an important service, you may want to continue to provide that service, like your pacemaker or your air traffic control. You don't just want to shut those things down. In that case, you may want to repair them. Our sponsor, DARPA, hired an outside company to try to break our system by introducing corruptions into a program that we were protecting. We were able to detect 80% of their attacks and to correct 75% of them. And then another piece of dynamic analysis work is work trying to determine which parameters are used in a read-only fashion and which ones may be mutated. So rather than having a single heroic analysis, which a lot of people have done in the past, a single heroic static analysis, which has interesting type system properties or a difficult pointer analysis, what we did is took a number of very simple static and dynamic analysis stages and put them together in order to outperform those other analyses. And finally, we have a lot of work in testing. We have some work in continuous testing. Your IDE today tells you if you've forgotten a semicolon or a closed quote, but it doesn't tell you if you write some code that will compile, but it's semantically wrong. And we want your IDE to do that. So the trick is we just run your entire test suite every time you press a keystroke, and then you know whether your tests have succeeded. The problem with that is your test suite may not run every time you press a keystroke, so we have a second technique called test factoring that takes your hour-long system test and converts into 1,000 one-second unit tests. And those are amenable to selection and prioritization. I'm not going to talk so much about these others because if you heard my other student, Carlos Pacheco's talk yesterday, he talked about feedback-directed test generation, which is an outgrowth work done here with Tom Ball and Shivendu Lahiri of some previous work on trying to predict whether a particular execution that doesn't violate any assertions is in fact erroneous. So let me get back to the main event. So I'm very fortunate to have worked with three exceptional colleagues, Philip Guo, Jeff Perkins, and Stephen McCament, on this work for dynamically inferring abstract types. So let me tell you what I mean about this. Here is a piece of code that is computing how much your order costs in some online marketplace, say. And you'll notice that we have just a few declared types. In particular, there are lots of instances of int here. And yet, these different ints mean different things. In particular, in a program, some of your ints may be file handles. Some of them may be counts of something. Some of them may be characters. Some of them may be indices into an array. And yet, they're all just declared as int. How can we determine which of those are the same type, which of those are related to one another, which of them are unrelated to one another? So that can improve subsequent analyses and it can improve understanding. So the problem is that we've used a few declared types for conceptually distinct values. What we really wish the program had written was something like this, saying that the result of this is a quantity of money, and the arguments are distance and two other types of money, and we also have some times in here. If you were to use type defs in C or structs in C#, then you could do this, but programmers may not have done that. How can we reconstruct that information or reconstruct it in a language where you don't have that kind of language support? So I haven't given you a formal definition, but essentially values have the same abstract type if they're conceptually similar and if they can be used in the same contexts. How are we going to infer these types? Well, essentially, the programmer has already embedded in the program a tremendous amount of information about the values that it computes. What we want to do is learn that information from the program. And in particular, if we have two values that are operated on together, for instance, you say a plus b or x less than y, then the programmer is saying to you that a and b have the same type and x and y have the same type, because it wouldn't make sense to add them to one another if they had different types or to compare them to one another if they had different types. And after we computed this for the values, then we say that variables have the same abstract type if their values do. So that's essentially the whole idea. Okay? So what good are these things? Why would you care? So if you want to understand a program, then the abstract types indicate how different variables relate to one another. And we have a case study that demonstrates that this is effective in helping programmers. If you're trying to develop a program, then you can compare what you believe the types are to what the inferred types are here, and you can find errors. In other words, places where what you've written in the code does not correspond to what you intended. And if you're doing automated analysis, often tools are intended to operate on variables of the same type. But if you have lots of variables that are all declared as the same type, then your tools may run too long, but much more seriously, they may provide a lot of false positives because they're comparing things that they shouldn't be comparing. And because the abstract types are finer than the declared types, you're able to overcome both of those problems. Okay? Yes, question?
What is so special about plus? Let's say consider division. Suppose you have distance and time. Then by dividing distance by time, you get something else. And distance and time obviously different.
Right.
Now,
Okay.
if you add, you may have so many feet and so many inches. So you can add even for addition, you may have.
So if you're adding feet and inches, I think that's probably a bug in your program, and we would, because maybe you could add feet to inches to feet times 12. That might be a sensible thing to do, but not adding feet and inches.
Somebody is 5 feet and 5'10".
But I mean, let me address your other. Yeah.
I mean, isn't what you're saying that plus by itself is not sort of giving you enough distinguishing power?
Right, exactly.
But I imagine what Mike might do is, like, if he sees that something is multiplied by 12 on a consistent basis, you might infer a conversion of some sort? I mean,
the technique that I'm going to show you does not do that. Oh. But Yuri has brought up an excellent point, which is what I said on the previous slide was value interactions unify their abstract type. So what is the definition of an interaction among values? And in fact, our implementation is parameterizable with respect to that. And we actually have 4 different things implemented. One of them gives you just data flow. Another one also includes comparisons. Another one includes scientific units. So it does not include things like multiplication and division. And the last one includes all operations. So it might clump together, for instance, everything having to do with physical quantities. And then separately, everything having to do with files. And we've done some experiments to suggest that the last one is best, but let me defer that until later. That's actually one of my backup slides, but if I don't bring that up, please remind me. But it's a good point, and the issue is, for different purposes, you may want to have different definitions of value interaction. Very good. Other questions? Okay, great. So let me restate the problem. We want to automatically infer the abstract types for a program. This builds on some previous work that was a static analysis. And the static analysis did a similar kind of thing, trying to observe which variables were used together. It cast this essentially as ML type inference, and there was polymorphism to try to regain a little bit of context sensitivity. But the analysis turns out to be relatively coarse. And this is a fundamental problem of a static analysis that can't do a perfect pointer analysis. So for instance, because it's a type system, it's flow insensitive. That means every variable has only one abstract type throughout the execution. But often, a temporary variable or buffer is used for different purposes at different points in the program. Another problem is because of the limitations of the pointer analysis, it confounds values that are stored inside of arrays. So these are just a couple examples of the sorts of imprecision that it suffers from. Our system turns out not to suffer from any of these sorts of imprecisions. And what we've done is instead, we have a completely different algorithm, though based on a similar idea, that's a dynamic approach instead. So the technique then is we want to observe the interactions between values to infer types for the values. That's the first stage. And the second stage, but we want to report in terms of variables, because those are the quantities that a programmer understands and can use. So we merge the value types to obtain types for the variables. And I'll talk to you about that. We have 2 implementations, one for binaries for x86 and one for Java bytecodes. And we have an evaluation that considers the accuracy of our system, its aid in program understanding, and invariant detection. So this is an outline of the rest of the talk. And now I'm going to discuss the technique first, which, as I mentioned, has two stages. The first computes value interactions. In other words, computes types for values. And then it converts those to types for variables. So the way that the system works for inferring types for values is that it maintains these so-called interaction sets of values. An interaction set says these values have interacted at some point during the program, and therefore we assume they have the same abstract type. So how do we create a value? Whenever you have a new value, place that in a singleton set. And how do you get new values? Well, anytime you execute a literal in the code, like you see the value 42, that gets put in a new set. And if that's inside a loop and you run around the loop a million times, you get a million different sets, one for each instance of 42, that you execute dynamically. If you read data from a file or have user input, again, those are new values, and they get put in fresh sets, in their own sets. And then when two values interact during execution, which we can think of as being some operation, but it's parameterizable, then we merge their interaction sets. In other words, if I see that X is in a set containing X, Y, and Z, and A is in a set containing A, B, and C, and I ask if X is greater than A, then afterward, both of them are in a single larger set containing A, B, C, X, Y, Z. So what are the value interactions? So we consider all binary operations, and the assumption is that these interactions convey some programmer intent, because the programmer wouldn't have made two values interact if they really had different abstract types. So let me give you some examples. And this is using the coarsest definition that makes the smallest number of abstract types, and each abstract type is as large as possible. So suppose I say your profit is your revenue minus your cost. In this case, what we're going to do is put all three of these into a single abstract type, because these two things are being subtracted, so they must have the same type, and the result has that same type. For a comparison, like is when if my score is greater than your score, this greater than puts my score and your score into the same interaction set, but is when is not put in the same one. This is a Boolean value. It really has nothing to do with the scores. And for logical operations, like the double ampersand logical AND, we don't do any merging at all. We leave those two things in separate sets because they don't necessarily have anything to do with one another. So let me give you a concrete example of this. Here's that same piece of code that I showed you at the very beginning. So suppose we have a call in your code somewhere, total cost of shipping something 3,000 miles that costs $50 and the tax is $3. So the first thing that we do is to have three different values here, and they're each in their own interaction set. Now, I've marked these with variable names up here, but those are purely to help us understand and follow what's going on. There's no analysis being done of variable names at this point. Yes, question?
It seems to me that you're inferring something that is at least a hierarchy of two levels, which are dimension and unit, right?
Mm-hmm.
Like price can be in dollars or cents, for example. And you're sort of flattening this into what you call types. Because, for example, time would be a dimension, while year would be a unit, right? And here, miles is a unit and price is a dimension, for example. So,
sure.
And I think this usually, in the literature, at least the proposals to extend languages, programming languages with units and dimensions, these two levels appear. And I think your operators, some of your operators change unit and some of them change dimension. So have you taken this into account and made a decision to flatten this?
So you're right. The set of operators that I've shown you so far are conflating. They're not respecting units. This is not a units analysis. We've actually designed a units analysis that is similar to this, both a dynamic and a static one. And it worked well, but we fundamentally don't believe that it's of as much use practically as this. So if you want, so why don't I just go to that last slide of the entire talk. Whoops, oh, that was a failure. Okay. Is there a key I can press? Does someone know PowerPoint here?
End, bro.
End? Cool. Okay. So what kind of modes you want for value interactions? So remember, what I said was interactions merge abstract types. And what kind of abstract types do we want? One possibility is that we want them to encode all sorts of information about dimensions and units. Another possibility is that we choose to put those things together. So we had one big clump for physical quantities, or one big clump for concurrency-related quantities. So we have 4 modes in our system. One is for data flow only. And so, for instance, if you have this kind of assignment, then the value gets moved over here. In fact, nothing has to happen because we're just operating on values. And that means that every value is its own type, and 2 things have the same abstract type exactly if value flowed from one location to another. The next thing you could do is to add comparisons, so that if you do this kind of comparison, then you merge those. A third thing that you could do is you could have plus and minus, but not things like multiplication, division, or shift. And in this case, we would merge profit, revenue, and cost, but we wouldn't do something like velocity, distance, and time. And this will give you scientific units. What we'll end up giving you is the clumping will be right, but one thing I want to emphasize is what we end up telling you is these 50 variables, they're related. These 7 variables, they're related, and they're not related to those other 50. But then it's entirely up to a programmer to interpret what those things mean. And then the final mode, which is our default, is all arithmetic. So these things would get put together. And I've ordered these from the largest number of abstract types, each of which is smallest, to the largest abstract types. So we showed all of these to people, and we ran all of them through we gave the results to a subsequent analysis. We found that people actually preferred this last one, even people who were working in a program that used scientific units. And the reason is people found it much easier to divide up groups that were too big and much harder to put together groups that were too small. It's possible that in certain circumstances, though, you'd want to use one of these other definitions. Yeah, Joseph.
It could be that there's an intermediate stage as well where you're kind of tracking sort of rational units.
Mm-hmm.
I mean, when you divide something by b, then you're kind of keeping the fact that it's sort of type A by type B, and that might have some value, right?
Possibly. I think that our implementation, so we use some implementation tricks to make this not fast, but not dreadful. And I think those implementation tricks would not work, and our performance would get dreadful. We'd have to actually have to pay attention to optimization then. Okay. Great. Okay, so we were right here. Good question. So we have these 3 values, and each one is in its own interaction set so far. So let's execute the next line. We've created a new value, so we put that new value in its own interaction set. Now when we execute the next line, first we create a new value for 1,000, and then we merge that with the value for 3,000 because we see them being compared. Now we create a new value for 2,000 and merge that with the value for year because we see them being compared. And finally we do the logical operation, which does nothing. Now we're on the next line, and we've created a new value and put it in its own interaction set. On the next line, we add price to tax, which merges those. And then we add that to shipping fee, which merges all 3 of those. And finally, we return that value. And that's merged with the others. Okay, so that's the final result then. What we end up with is these specific values are clumped into these 3 interaction sets. So how do I convert that to information that you could give to a programmer or to a subsequent analysis? Well, we need to convert this into variable types. And essentially, 2 variables are given the same should have the same abstract type if the values that those variables hold have the same abstract type. Yeah.
So it's not the sort of numerical value, but sort of that specific instance of that.
Yes,
Like, yeah.
that's exactly right. So I could have many instances of null in the program. They don't all have to have the same type. I mean, and that's in fact why if you're going around a loop, which had, if you go around 1,000,000 times in a loop, which has the number 42 in it each time, or the value null or something, we give those separate, put those in their own unique interaction sets. Right. So in other words, now we see that we have this called the total cost. These two values were in the same interaction set. And that means that price and tax must have the same abstract type. So essentially, every time you execute a function, you say, for every pair of values that have the same abstract type, their corresponding variables. For every pair of actuals that have the same type, their corresponding formals must have the same type. So essentially, just copy that information from the values to the variables. Yes, Yuri?
Something caught my attention. So suppose you have a variable in a loop.
Mm-hmm.
You go once, it gets value 7. You go second time, it gets value 11. So since it's the same variable, why should we create different sets of 7? Shouldn't it be the same?
Okay, so the question is, suppose you have two executions of a loop, and on one execution, a variable is given some value. On the second execution, that variable is given a completely different, unrelated value. If you had a type-based system, then every variable has to have a single type. But we have a value-based system, and I have a slide coming up very soon that explains why we think that that's a little bit better. Essentially, if you reuse a temporary variable for two different purposes, or if you have two different code paths that do slightly different things, then you won't conflate those. So our implementations only compute this at function entrance and exit points, just because we want to give specs.
Suppose it could be something like an arithmetic progression or something.
Mm-hmm.
So in that situation, would there be conflation?
Absolutely. So for instance, if x was first 7, then on the next iteration you incremented it, so it was 8. Well, what you do is you'd create a new 1 with a fresh type. You'd add that to 7. They would get conflated, and now your variable is 8, but it has the same type as it had before. It just is in a bigger set. So the analysis output then says miles is in one set, price, tax, shipping fee, and return are in another set, and year is in another set. And this is the actual beautiful textual output from our tool.
So what happens if I call total cost more than once?
So if I call total cost more than once, then the next time I call it, this is the initial estimate. And if on that second execution, suppose somehow return and year had been, the value for return was somehow conflated with the value for year, then I would merge this and I'd get one big set as my summary for total cost. So each time I execute it, I merge in any new information about common abstract types from the values into the variables.
Okay. The interesting case that makes me think of is if I call a function that's get an integer from the configuration file.
But that's okay because you're reading from a file, so that's going to be a fresh value. And it's not going to be...
I'm worried about the return value of the function, not the value that I'm reading from the file.
So things will be conflated maybe at the return value for that function, but not anywhere else because we continue to track values, not variables.
Okay.
Yeah.
So is this just intra-procedural, or do you use, for example, if I pass the same argument for price and tax, would you then...
It's a dynamic analysis, so we run the entire program, and every value, at every moment, every value in the program is in some set or another. Eric?
So how do you deal with container structures? Are you tagging all these low-level scalar values, or do you have some kind of...
Every 32 bits in the program is in some interaction set.
Okay, that includes pointers.
It includes pointers. But really, what we do is, since we have a dynamic analysis, we follow that value into the container. And when it's sitting in the heap, we still know what interaction set it's in, because we're tracking the value.
Right, like said, you've sort of tagged that value so everywhere
Yes.
it goes.
Every value, I mean, so that's the actual implementation. The implementation is we have a tag for every word. Every word of memory has a tag, and that tag indicates what set it's part of. And then we have a union-find data structure, and we merge the tags. Yeah?
So maybe you should tell us what you're going to do with this stuff. Because a lot of the questions are motivated by, we're thinking, well, maybe you're going to assign these types that you're showing, right? And if you want to do that, then a lot of these questions have different answers, right?
For instance, if you wanted to type check based on this, for example.
If you wanted to assign, as you do there, if you wanted to assign a local, an actual refined type, then it doesn't make sense to have multiple sets. Because you will have to pick one in the end, right? So maybe a lot of these questions would go away if you told us what you're actually going to do.
Right. So right. So I should say two things. One is that we've actually implemented several different policies for this that I'm not going to discuss all of, and some of them don't have this property. And second is we're not planning to feed this back into a type inference, though it would probably be better if you restructured your program in such a way that you could type check it, because then you wouldn't be using variables for completely unrelated purposes. We're really going to feed this into a subsequent dynamic analysis or give it to a person to help that person better understand their code. And that's the next section of the talk. Let me first discuss why we're tracking values instead of doing a static analysis. So the nice thing about this is that it naturally achieves context sensitivity and flow sensitivity. So here's an example of a routine strlen that takes the length of a string. If we were just tracking, so we start out saying name is in one set and address is in another set. So if we're just tracking variables, then first we call strlen on name, and that says, oh, name is in the same set as arg. That's fine. Now we later have a call to strlen of address, and that says arg is in the same set as address, so all three of them get put in the same set. Now, if you add context sensitivity, you can get around this particular problem. I just gave you a really simple one to show you what's happening. A dynamic analysis doesn't have this problem because first, when you call strlen of name, then these are just variables that are pointing to this value, which is in one set. And then later, we have these two names, these variables that are pointing to this other thing that's in a different set, and they don't get merged. OK, so I'll talk very briefly about the implementations, then I'll get to the evaluation, which will show whether this is good for anything. So as I mentioned, our implementations really just maintain a 32-bit tag along with each value. And the tag is a pointer into a union-find data structure so that you know for every pair of values, you can quickly determine whether they're in the same interaction set. So we instrument the program at load time so that it creates tags whenever you create a new value, so that it copies tags whenever you do an assignment, and so that it unifies interaction sets of tags whenever there is a qualifying interaction. We have a system that works on x86 binaries. It only works under Linux, and it works on C and C++ programs that have been compiled from C and C++ code. We use the Valgrind toolset to do our instrumentation. And there's a tag for every register and a tag for every byte of memory. It includes a bunch of optimizations. It has a garbage collector to garbage collect the extra tags. We also have a system for Java programs. We do bytecode instrumentation using this BCEL library. And there's a tag for every primitive variable on the stack and for every primitive field within objects. And we didn't have to implement our own garbage collector there, which was nice. So that's all I'm going to say about the implementations. So for my evaluation, I'm going to talk a little bit about how accurate it is. And then I'm going to show you just two. Oh, yeah, Eric.
Can you tell us how much slower the implementation makes things?
Oh, gee, I didn't really want to talk about the implementations. So here we're using Valgrind. As soon as you turn Valgrind on, you pay a factor of 10. As soon as you do anything interesting, you pay another factor of 10. And that's about what we're paying. So it's painful, but not completely ridiculous. And this is not optimized for speed. There are certain things we could do that would be much, much better. So for instance, every time you perform any operation, we add a second operation which of course costs you time, costs you register pressure, costs you in the code cache, that operates on the tags. It would be much better for a single basic block if we did a static analysis and figured out this is what the basic block is going to do, and just quickly use those, and then we could run the rest of the basic block at full speed. We haven't done any of that sort of optimization.
Sure, first you want to see what's useful.
What?
I said, of
Yeah,
course.
right. And the Java version, the overhead is not nearly as bad. I don't have off the top of my head how much slower it is. That's mostly because the JIT is taken care of, well, because you don't have to worry quite as much about register pressure, and because the JIT is taking care of optimizing quite a bit of it for you. There is, the painful thing here is that we're keeping an extra stack and manipulating that stack. And of course, all the manipulations of that stack are using the real stack.
Yeah, don't worry about multi-threading and multiprocessor.
That's correct. We just haven't considered those issues at all. Okay, other questions? This is good, thanks. Thanks for keeping me honest. So now I'll talk about the evaluation. So we wanted to evaluate the accuracy of the system, and we took a relatively small program. And the reason we took a small program is that we exhaustively analyzed it by hand, including doing a perfect omniscient pointer analysis by hand. There are 21 global variables in this anagram generator program, and I've put them all right here. The hand examination of the code and the comments revealed that there are really 10 abstract types. So examples of these are an abstract type for word, which is really pointer to characters containing word, and an abstract type for word count. So then we ran our system, and our dynamic analysis found 11 types, not 10. So it got many of them right, but here the abstract type for word length was actually split into two by our dynamic analysis. And the reason was that two variables of that type never actually interacted in the program. We also ran the LACWIT program, which is static analysis that does this ML-style type inference, polymorphic type inference. And that found 7 types. It got the 6 things that the 6 abstract types of size 1 correct, and then it lumped every other variable into a single abstract type. So let me just give you one example of something that it got wrong. There are elements of the argv array, that's the list of arguments that the user has typed. So you call it like this: wordplay minus d depth, you pass in the word, pass in another flag that gives the dictionary. Now, all of this is in a single array, and so the analysis assumes that all the elements of that array must be of the same type, and then you compute the depth, you pull the depth out of that, and you pull the word out of that, so those must have the same type, so everything else gets conflated. Eric?
Although presumably you could do some filtration saying that if they're two different system types, they don't really belong in the same one of your types.
Right. So the thing about LACWIT, both LACWIT and our system, is that it first completely ignores all declared types and then tries to infer a new set of types. In fact, if you look at some of these, I have a paper that can give you the details. Some of these abstract types actually contain both ints and int pointers in the same abstract type. So you really do want to ignore the system types. Now, if you wanted to, you could only look for a refinement of the existing declared types. And this particular problem, you could say, okay, we know argv is a problem, so let's special case argv. But this is just one example in a tiny program, and there are going to be lots of other similar examples that come up.
For sure. I mean, it's just C programmers do conflate instant pointers and so on, so you have to conflate them. On the other hand, they don't tend to conflate floats and pointers.
Right. Yeah. So these were both actually ints, though, because word was a pointer. But yeah, I mean, if you believe that all you're trying to do is refine, I agree. You could use. I mean, we've already said programmers encode a lot of information in the program, and we want to take advantage of that. We could further take advantage of all the declared types as well if we chose, and it's a good idea. I agree. Yeah?
I think something basic. So you classify values.
That's right.
But at a certain point, you jump to classification of variables.
Yes.
What is the transition?
Okay, I'm sorry, that went too fast. So that was here. So we classify values. However, we want to compute variable types at certain points. Our implementation says, I'm interested in function entrance and exit points, though there's no fundamental limitation there. So every time you encounter a function entrance point, you look at all of the actuals. If any pair of actuals has the same type, then merge the types for those formals. And then you just do that every time you execute that particular point in the program. Yeah?
You also do this for global variables at program entrance and exit points?
Yes. So we consider all global variables to be parameters to every procedure.
Okay. And if I'm the caller and I have a local variable, so there's a function entrance when I'm calling it. Are you classifying my local variable at that time?
No.
Okay.
So what we're trying to do is generate something that looks like a spec that says, yeah. Wait, there's no reason you couldn't do that. We haven't found it useful at this point. Okay, great, good. Other questions? Okay, so that's the accuracy evaluation. Would have loved to do this on bigger programs, but it was a lot of effort to exhaustively analyze even something that was small. We did spot examinations of bigger programs, and everything looked right to us. But there we're only spending half an hour, an hour on each pair trying to figure out if it's exactly right. So let me talk to you about how this is useful in program understanding. So we ran 2 case studies with other researchers at MIT. In the first case, it was a computational biologist who was looking at an RNA folding program that was written in C. And the programmer had just refactored 55 int variables of abstract type energy. It was actually activation energy, to be of type double. And it took him about 16 hours of work to find the energy variables among the hundreds of ints. And he reported that it was tedious, and he had to go through the entire program a couple of times before he was confident enough of his correctness that he didn't want to work on it anymore. So we took a single 100 base pair RNA sequence when we ran the folding program on that, and we found that there were, out of the hundreds of integers, there were 60 int variables that were in one abstract type. So the programmer looked at this, and he found that there were 5 variables that had nothing to do with energy that were used inconsistently in some rather complex initialization code. Because, they were there, you might as well reuse them. They're not going to be using them later. And why waste extra variables there? So the programmer was able to pretty quickly see where these were used, how they were interacting, and that they didn't matter. And now our result was exactly consistent with the 55 variables that he had. So the programmer became confident that he had, in fact, gotten this right. And he said unfortunately, we caught him right after he'd done this. I wish we'd caught him right before he did this. But he said it still probably would have taken him an hour or 2. But that would have been much better than the 2 full days of effort. So another programmer had a support vector machine program that was written in C. He was porting it to a hardware implementation, actually. And he wanted to understand how the different variables were used because he wanted to give different types to the ones that were used in different ways. So he was in the middle of this porting task, and we gave him this. There was a perfect correspondence for variables that he believed stood for error bounds. There was not a perfect correspondence for this variable buffer that he knew how it was being used, but our analysis said that it was actually being used in many other ways. So he reported a bug to us. And it turns out that, in fact, that variable was used pervasively all over the code in ways that were not at all apparent to him. And he was able to revise his understanding of the code and avoid incorrect porting. So far that's an accuracy evaluation and an evaluation of use by programmers. Now I'm going to talk about how you could feed this into a subsequent tool. So as an example, I'll use dynamic invariant detection. There's this tool called DICON that uses machine learning to infer relations between variables. For instance, it might report that tax is less than price. And the way that it does this is it observes your program running, collects all the values that were held, all the tax comma price pairs, and then if tax less than price always held, it reports that. And it checks tax greater than price, tax less than or equal to price for every pair of variables in the whole program. Now, that sounds terrible, but luckily it only compares variables of the same type. That's still actually pretty terrible because it might report something like miles is greater than tax, since both of those were integers. If you were to use abstract types, you can avoid doing this check. And that's useful for two reasons. One reason is that it makes the system faster because you don't have to check over unrelated variables. That's actually not important. The really important reason is that it avoids false positives. It avoids giving reports like it used to do. It used to gleefully report, this pointer is greater than this Boolean, which is true, but is completely useless. Right, and so I've already told you why we care about this. So how did this help? One thing that you can do is you can use the representation types. For instance, this would conflate things like character and byte, or it would conflate int and long. Another thing you can do is use the declared types, or you can use the abstract types. And you can see that I've used the representation types, which is the default for DICON, because it wants to opportunistically compare as many things as possible. Because its whole purpose is to serendipitously tell you things you didn't know, not just to verify things you already did. So this is the baseline. You can see that using declared types reduces the time and memory sum and gets rid of 30% of the output. Abstract types improve the time and memory a bit more, but they reduce the amount of output by a factor of 6. And we examined some dozens or hundreds of the things that were removed, and every one of them was spurious. But we didn't investigate millions, which is how many were actually removed. So these are the averages for 8 C and Java programs. The biggest improvements came on the biggest programs. We didn't run it on anything really big, programs of less than 100,000 lines or so. We had to instrument the whole thing, but we only examined the output. We only converted it to variables for a small portion, but the analysis actually ran on the whole thing. And the static analysis didn't scale up beyond programs of hundreds of lines. So what can we take away from this? What I've suggested is a dynamic approach to figure out what the abstract types in your program are. So it first operates on values, and then when it's computed which values are related, it can translate that to variables. It's conceptually simple, it's precise, and it's effective in practice. We have implementations for both C and for Java. And our evaluation suggests that at least for the set of programs that we looked at, that it's accurate, it produces results that are the same as what a programmer would want, that it assists programmers' understanding of code, and that if you feed this to another tool, that it can improve both the performance and most especially the accuracy of that subsequent tool. So I'd be happy to take further questions that weren't asked during the talk. Yeah?
I just, more of a comment, I guess. It seems like your philosophy here is to basically ignore the way the program was written and understand just the way it's run. You think that's an accurate way to sort of state your approach here?
So we're ignoring the way the program is written in the sense of ignoring the types that were written in it. But we're not ignoring the computations that are performed in it. I mean, in particular, the programmer has compared certain variables to one another. And it's exactly that we're trying to extract.
Right, but you're only checking the comparisons that are executed as opposed to the ones that are actually,
yes, that's right. So I should point out, this is a dynamic analysis, right? And that means that it may fail to unify some things because you didn't execute one particular path of the program, or some particular data dependence didn't exist on a path you did execute. Right. That's absolutely correct. Right. That's a limitation.
Right. Well, I was saying it's a limitation. It's just like the flip side of that is that you get to do the right thing for every nasty programmer trick that ever gets done. Right?
Yes.
Which is where a lot of these sort of static analysis things do fail, which is when the programmer does something evil and nasty, and then that's cute.
Yeah, I mean that's exactly right. So we wanted to use the static tool.
Right.
I mean, we were motivated by this daikon example because we were trying to make daikon better. We tried to use the static tool, and it didn't work out very well for us. And we said, well, that's a static approach. Why don't we try a dynamic approach? Right, so, sure. I mean, my belief is that for every static analysis, there's a corresponding dynamic one, and vice versa. Sure. And the dynamic one tends to be precise. It may be more efficient, especially if the static one is trying to do some kind of complicated reasoning. And on the other side, the static one can be sound because it can be conservative, but it may be very imprecise then. So what is the trade-off, and which ones are useful for different purposes? Sure. And so what we found was that for these particular purposes anyway, the dynamic approach was competitive and was even better for some uses. Sure. Yeah, Joseph.
Just to apply this to a completely different domain,
sure.
It might be interesting to see whether this can be applied to databases.
Mm-hmm.
You know, where you have a whole bunch of SQL that's been written and the tables, and might just be interesting lines where there's again comparisons and so on.
I see. So you're saying, suppose I have a database and the schema is either not written down or you don't believe in it.
Yeah.
Then
just same old.
Right. So could we figure out what the relationships among the rows and the columns are?
Based on what queries get typed in.
It would actually be interesting, not just based on what queries you get typed in, but then how that information is used once it's flowing through the program. It would be interesting to do a combined database and program analysis, because often you pull a few things out of the database, do a little bit of business logic on them, and then you either shove them back into the database or you make a report.
Yeah, exactly. I think it's useful.
Yeah, my only worry would be how bad is, I mean, you'd have to be a good systems hacker to keep the overhead down. I think you could do that. Yeah?
You promised an example where you have a variable in a loop, and you come again and again to that point in the loop, but you don't want to unify mathematically the values.
Okay, well, I mean, so here is a contrived example. I apologize that it's contrived. It's no more contrived than some of the C code that the programmers write. So
just have a flag, inside your loop, right?
Yeah.
So you start out with Boolean first equals true, and then loop if first do one thing and else do something different, right? And then all of a sudden,
right. So here we have an if, and of course you don't want to, we're declaring. In fact, you wouldn't even do that, right? You'd put it outside. And then no one would know whether it's a loop carried dependence or not, but they should be able to figure it out. And then we just have two different pieces of code here.
I'm sure I haven't seen that today.
I mean, so I'm completely sympathetic to the notion that if your code is well written, then none of this is necessary. And this code should have been rewritten this way. And then it would have been clear that these are completely different variables and the conflation wouldn't have mattered. But our analysis could indicate to you that that would be a possible thing to do and a legal thing to do.
But these two occurrences at different points in the program.
Mm-hmm.
So I expect what variable at the same, you come exactly to the same point in the program.
Oh, so the a call to strlen, for example, is an example of that, right? You're probably going to pass many different types of strings to strlen, but you don't want to conflate all instances of the formal parameter to strlen. Yeah, Lee.
So if you're working with APIs that have a lot of optional arguments,
mm-hmm.
and you get a lot of zeros and nulls, and you also pass those optional arguments onto other APIs, then will you often conflate those?
No, and the reason that we don't do that is because there are different instances of 0, right? They're in different registers or different places on the stack, and each one has its own tag. And you had some call that was like foo of something 0, 0, 0. And in this case, each of these gets its own fresh tag, or if they're copied from somewhere else. No. Right, and that's why it's crucial that whenever you create a value, and this is a constructor for ints, that new value gets put in a separate set, or that it gets a fresh tag. Same thing, just the implementation detail.
Does Java's small int cache entirely confuse?
No, because our instrumentation takes care of that.
Okay.
Right. That would be a problem, but we've addressed it. Okay. Well, thank you very much. I really appreciate the questions. That's what makes a great talk.